Hello everyone. My name is Xue Chen. It's my pleasure to represent our research team to share our most recent work with you all. The research work I want to share here is the LRDNet, a lightweight real-centered detection network for cross-domain face forgery detection. If you have any questions in my presentation in our paper, you can contact me at my email address. I'm willing to answer all your questions. We start from introduction. Modern generative AI can create extremely realistic fake images. For example, the Stable Diffusion. We can use Stable Diffusion to easily generate some fake images. It's very cheap and everyone is able to generate fake images. The fake images reduce trust in digital media and can be used for identify fraud and manipulation. So it bring severe security threat to our daily life. Traditional forgery method relies on simple artifacts. It's easy to detect, so we can easily use a transformer, a basic transformer, or a basic convolutional neural network to do this kind of detection. While for the AI-generated images are much more realistic, it's a bit hard to detect which image is fake, which image is real. Let's have a look at these three images. I gave three image samples over there. All of them are generated by generative AIs. It's a bit hard for human eyes to detect, to say which one is a real, which one is a fake. So new detection methods are required. It is urgent. We need to propose a novel method to detect the AI-generated images, to detect the fake forgeries. So another challenge currently we are facing is the cross-domain performance. The cross-domain performance, just like the image I gave it here. In domain is we use the red color as the training set, and we use the red color as the test set. We use green color as the training set. We use green color as the test set. The cross-domain is we use red color as the training set, while we use green color as the test set. So this is what we call the domain, a cross-domain. The cross-domain detection evaluates whether a model trained on a forgery domain can generalize to other domains, including different generation strategies and different generative AI models. For example, the different generation strategy include the face swiping, face editing, or something. We call them as a different strategy. So if your model trained on the face editing, can you use your model to solve the face swiping problems? This is a cross-domain detection. Another example is if your model trained on the Stable Diffusion generated images. So if you want to use the model to detect the image generated by ChatGPT, can you do this kind of task? This is a cross-domain performance. We want our model is generalized enough. We want our model is able to handle the unseen strategy, is able to handle the unseen AI models. So it's better to consider the cross-domain performance. This is our model. We call it as LRDNet. This is a pipeline of our model. We start from the left. This is our input image. We resize our input image to the 224 by 224 by 3. The next step is we go through a wavelight guidance module. The reason is a lot of previous research already demonstrate if you analyze the image from the frequency domain, we can have a better performance. So the first step, we apply the FFT to get the frequency domain image, and we use the frequency domain to generate the attention guidance. So in the future detection, we will use the frequency domain feature as a guidance to find the focus, to find the attention. The second module is the spatial backbone. The spatial backbone, we select the MobileNet as our backbone because we want to have our solution is a lightweight solution, so we do not use a heavy network as a backbone. We select the MobileNet because it is simple enough. And the MobileNet is guided by the attention. The attention is generated by the wavelet guidance module. So we use the attention to find the focus. The next, we concatenate our features. We analyze the features we extract from the backbone. We do a linear layers, we have a dropout, we have another linear layers, and we generate the final embedding. And the real center embedding, we have a real center embedding solution like this image. In the center of this circle, this is the real center. And our detection is if the embedding is near to the center, we believe this is a real image. If the embedding is far away from the center, we believe this is a fake image. So we use the distance to define this is a real or a fake. This is our loss function design. Actually, for our loss function design, we have 3 components. The first one, the loss function CLS, this is a very basic cross-entropy loss. We use the cross-entropy loss to say if our prediction align with the label. The next, we maintain a real center. The real center, this is a definition. This is a long equation. The ultimate goal for the real center is because we maintain a real center. So for each sample, we need to update the position of the center. We need to update the item for the center vector. The next one is the draft. So we want to make sure the real center, the real image and the fake image, they have a large separation. So we have the draft concept over there. So this is our loss function. We have 3 components. And this is a dataset we use. We have a DIFF diffusion generated phase forgery dataset. This dataset is widely used in related work. The reason we select this one is it includes a lot of images, and a lot of baseline models use this one as benchmark, so we can easily make a comparison. Next one is for the dataset, it includes a different generation strategy and different AI models, so it's easy for us to examine the cross-domain performance. Just like this image, the left one is an original image, this is a real one, and we can use 3 different strategies to generate fake images. Like this column, this is a text to image. Text to image, so the text here is a prompt. So we give a prompt to the AI tools, and the AI will based on our prompt to generate images. We call it as a text to image. The second one is image to image. So we give an image to AI tools. And besides the image, we also give some prompts where we want to make the modification. It will generate another image. This is image to image. The last one, face editing. So we edit the face. And for our experiments, first one is our in-domain performance. The last row is our current solution. So we have almost the perfect solution. And maybe you already noticed for the RCDN, for the DIRE, for the efficient net. So they also have a very near perfect performance. So it demonstrates for our for the current solution, it's able to handle the in-domain forgery detection. While for the cross-domain, so we can notice a huge gap. The exception, the first matter exception, it has almost perfect on the in-domain, but for the cross-domain, the performance drops to like 87. The efficient drops to 88, 90, or 83. So for these examples, it demonstrates for the current solution, they focus on the in-domain performance, while for the cross-domain performance, they underestimate the importance. The last row is our performance. You can notice, although we still have a lower performance when compared with the in-domain performance, but we still beat the other comparisons. We have a more than 90% accuracy, so it demonstrates our model is more generalized when compared with other baselines. And for our model, we also we will also want to make our model is lightweight, so we also examine the efficiency of our solution. We compare our efficiency with the RCDN algorithm, and it demonstrates we have almost 8 times faster for the training time, and for the testing time is almost 10 times the original efficiency. Like for the RCDN, it costs 2 minutes and 15 seconds for the test set, while for our solution, we use only 13 seconds as the efficiency, as the time cost. So this group of experiments demonstrate we have a better time efficiency. Our contribution, we have 3 aspects. The first one, we propose the LRDNet. This is a lightweight and real interface for redetection framework. And for our network, we are able to handle both in-domain and cross-domain. Our model is good for the accuracy and is generalized. The second one, we design LRDNet. We want this is lightweight. We want to consider the computational efficiency, and the experiments demonstrate we have almost 8 times the better time efficiency. The last one is we conduct extensive experiments on the diff benchmark. It demonstrates we have a state-of-the-art performance. Okay, that's all of my presentation. Thank you for your time.